are they and how do you make them? I'd like you to pause the video and write yourself a definition of diodes. If you've heard multiple definitions, then feel free to write them all down. For the record, I came up with 3. The 3 definitions I came up with are 1. That diodes are two-terminal circuit elements that let current flow one way. 2. That diodes are two-terminal circuit elements with an exponential IV relationship. And 3. That diodes are metallurgical junctions between P and N-type semiconductors. The first 2 definitions both kind of say the same thing. That diodes are a circuit element with 2 terminals, and I've included the standard schematic for a diode over here. And that the IV relationship of a diode is kind of surprising. I've drawn an exponential curve on an IV plane here, and you can see that the current on the curve is high and growing when VD is positive, and the current is small and constant when VD is negative. As a result, the claim that diodes have an exponential IV curve and diodes only let current flow one way are basically the same thing. This exponential behavior is kind of weird though. My mental model for current conduction when I first ran into diodes is captured by this picture on the right, which says that electrons are accelerated by electric field, but that their maximum velocity is limited by bouncing off of atoms. So that picture makes sense, and I can believe that it'll lead to a linear relationship between I and V if the bouncing is severe enough to stop the kind of infinite acceleration of an applied electrical force. However, the model just says that materials are kind of mute obstacle courses for electrons, and a diode is just made of some material. So how does a diode know which way to let current conduct? How can we bake some sense of asymmetry into a material? Our third definition starts to get at that idea. It's different than the first 2 definitions because it speaks to what a diode is rather than what a diode does. So somehow these P and N-type semiconductors act differently than resistive materials, and we'll get to the bottom of that in these videos. To start solving the mystery of diodes, we should figure out what P and N-type semiconductors are. We start with a picture of intrinsic silicon, which is a pure silicon crystal. Intrinsic silicon is made of silicon atoms that have covalent bonds with 4 nearby neighbors. And I've drawn one of those lines as a dashed line right here, which indicates a bond that has been broken by thermal energy, so that a few free charge carriers have been released into the crystal. Half of these charge carriers are electrons that used to be tied up in the covalent bond. The other half of the charge carriers are called holes, and they require a bit more description. Holes arise because the absence of electrons in a crystal is chemically unstable, so other bonds in the crystal will shift around trying to plug that absence. This results in the absence of a bond appearing to move around the crystal, and we elect to treat that absence as a positively charged particle, or technically something called a quasi-particle, to simplify our modeling. This is fine, but thermally broken bonds are pretty rare in silicon. The covalent bonds that hold a crystal together are stable, so there aren't many charge carriers. For reference, there are about 10 to the 10th charge carriers per cubic centimeter in silicon at room temperature, which is much less than the 5 times 10 to the 25th atoms per cubic centimeter. That means that intrinsic semiconductors aren't terribly conductive, because mobile charge carriers are the source of conductivity, and they're rare in intrinsic silicon. However, it's possible to introduce additional carriers to silicon by doping it, which is the process of deliberately introducing impurities to change a material's behavior. For instance, injecting phosphorus atoms, which we see in this picture, into a silicon lattice will result in them displacing silicon atoms and leaving an extra free electron to roam around, because phosphorus has 5 valence electrons while silicon has 4. So they've just got an electron to spare that becomes a free electron. The fixed phosphorus ion that is left behind in the lattice has a net positive charge because it's lost one of its electrons, which is now free. Silicon with sufficiently many phosphorus atoms in it is called N-doped, where the N stands for negative charge carriers. Similarly, boron atoms have only 3 valence electrons, so they'll steal an electron from a neighbor to integrate themselves into a lattice, which will result in a free hole and a net negative charge on the boron atom. This type of semiconductor is called p-doped, where P stands for positive charge carriers. You can make a tight metallurgical junction between these materials, which just refers to the two materials being mechanically stuck together, like in good contact, by driving lots of n-type dopants into a p-type semiconductor as pictured here. One way to do this is to strike a phosphorus plasma above a piece of p-type silicon, then apply a DC bias to the plasma so that ions are just hurled straight into the surface of the p-type silicon. Once enough dopants accumulate, then the n-type dopants overwhelm the already present p-type dopants in the silicon that's being targeted, resulting in an n-type region that's called a well or a tub. The interface between this region and the p-type region is called a p-n junction, and we'll look closer at the physics of a p-n junction over the next few videos. There are lots of details with this process that would be fun to talk about more if we didn't have other pressing business. So, the exact number of different dopants at different depths is called doping profile, and real devices are made with much more complex doping profiles than this. It's also worth noting that doping with different materials and dopants can make a lot of interesting p-n diode-like devices, including common ones like Schottky diodes and Zener diodes, or weird ones like gun diodes. And I'm happy to talk more about that if you chase me down. So in summary, diodes have exponential IV relationships, unlike the linear resistors, capacitors, and inductors that we've seen before. Silicon diodes are metallurgical junctions of p and n-type silicon. You make p or n silicon with doping in order to generate more carriers in the silicon. And you make junctions by injecting ions into p-type silicon wafers.